Okay, so the next thing that we want to cover is the three different types of solutions to equations. So remember, we talked about this at the beginning. There's three situations that can arise when we solve a system of equations. The system could have one unique solution. And so this is the case with all of the examples that we've done in these lectures and in the worksheets so far. But the system could also have no solutions. This is sometimes called overdetermined or inconsistent. Or the system could have infinitely many solutions. This is sometimes called underdetermined. And so today what we're going to do is go through each of these different cases and talk about how we recognize it and how we form a solution out of it. So a system of equations like ax equals b, has a unique solution if and only if all of the following conditions hold. The number of equations is equal to the number of variables. So this means our coefficient matrix, A, is square. The number of pivots has to be equal to the number of rows or columns. So in other words, when we perform Gauss-Jordan elimination, the coefficient matrix is transformed into the identity matrix, because we eliminate all of the entries below the pivots and above the pivots, and what we're left with is an identity matrix. If this is the case, then the matrix A is full rank. This means that A has an inverse. We call A invertible or non-singular. All of these three or four things that we can say about a square matrix are equivalent. Full rank, has an inverse, is invertible, is non-singular. All saying the same thing. Okay, so the next case is this inconsistent case. So this is very specific. For a system of equations to be inconsistent and have no solutions, at least one of the equations is going to reduce down to the form 0 equals alpha, where alpha is non-zero, after performing Gaussian elimination. So our our row echelon form is going to look something like this, where we've eliminated using the pivots, and then we reach a row that has no pivots and all zeros below it, but the right hand side value is not 0. So when we convert this back to our system of equations, this last row means that 0 times x1 plus 0 x2 plus 0 x3 is equal to alpha, where alpha is a non-zero number. So that's a complete contradiction. That's saying that 0 is equal to alpha. Can't have that. So there are no solutions. There's no values for x1, x2, and x3 that will make this true. So here's an example of trying to identify an inconsistent system. We start with a system of equations, and then we make the augmented matrix, and we start to perform Gaussian elimination. So we're going to use this first pivot element in the top left corner to eliminate all of the elements below it. And so to do that, since they're all 1, we're just going to subtract row 1 from row 2, from row 3, and from row 4. So here I've done these operations simultaneously in one step. I encourage you to pause the recording and check my math here. And now, when we go to identify the next pivot, we find we have a 0 where we expect a pivot to be. And so we'll have to interchange a row in order to make this entry non-zero. So here we've swapped row 4 with row 2. And now we're going to continue and eliminate the entries below the pivot. So that's done just by subtracting the second row from the third row. 2 minus 2 is 0, minus 2 minus 0 is minus 2, and 2 minus 3 is minus 1. So we're almost done. We can actually already see the contradiction right here, because these two rows right here are telling us that if I multiply the third variable, right, this is for x1, x2, x3, if I multiply the third variable by -2, in one equation that answer should be -1, in the second equation it should be 1. So this right here is the contradiction. But we can go further with the elimination and go ahead and perform row 4 minus row 3 to eliminate the entry below the next pivot. So this next pivot is here, -2. And when we do that, we see we get a row of zeros, and then we have a non-zero element on the right-hand side. So now we see our contradiction. Since this is obviously impossible, we conclude that the system is inconsistent. So sometimes inconsistent systems are referred to as overdetermined. This is usually because there's more equations than variables. It's like holding too many demands for such a small set of variables. So this is precisely the situation we find ourselves when we approach linear regression. Because we have so many observations, we can't demand that all those observations lie on the same line. There simply won't be a line that fits them perfectly. And so since we can't find an exact solution, we have to try to get the left and the right-hand sides as close to each other as possible. This is done using the least squares method. More on this will be coming soon. Our final case is when we have infinitely many solutions. Let's consider the following system of equations, written as an augmented matrix, and its corresponding reduced row echelon form, after we perform Gauss-Jordan elimination. So when we look at this reduced row echelon form, we notice some things about it. First of all, there's a row that is completely zero. What does that mean? It means that one of our equations was completely eliminated using just a combination of the others. Therefore, it must have contained unnecessary or redundant information that was already captured by the prior two equations. You'll also notice that there's only two pivot elements. There's no pivot element in the third row. The last entries in this third column cannot be eliminated. When we see these entries that can't be eliminated, this is characteristic of what we call a free variable. So if we translate this back to our if we translate this back into a system of equations, we have x1 plus x3 equals 0, and then we have x2 plus x3 equals 0. So our answer depends on the variable x3. We can solve for x1 and x2 in terms of x3. So let's suppose that x3 is some arbitrary number. We'll say it's alpha. Then if x3 is alpha, it's clear that x2 must be minus alpha, and x1 must also be minus alpha. So our solution would be this vector right here. x1 is minus alpha, x2 is minus alpha, and x3 is alpha. And so if we factor out that alpha, we have that the solution is alpha times this vector here, minus 1, minus 1, 1. And so since alpha is just some arbitrary number, any scalar multiple, any value alpha, will work. So any scalar multiple of the vector minus 1, minus 1, 1 is a solution. Therefore, there are infinitely many solutions. So a system of equations, ax equals b, will have infinitely many solutions as long as the system is consistent, so you don't have that situation with a row of zeros and a non-zero number on the right-hand side. As long as the system is consistent and any of the following conditions hold. After Gauss-Jordan elimination, you have at least one row of the matrix with every element equal to 0. If the number of variables is greater than the number of equations. If one of the equations is a linear combination of the others. So this is equivalent to saying that one row of that reduced row echelon form is completely 0, right? Because in order to form the rows of that reduced row echelon form, what we do is we're taking linear combinations of the equations. And also if there is at least one free variable presented in the reduced row echelon form, which means that the number of pivots is less than the number of variables. In this case, we say that the matrix A is not full rank. So here's another example. Here I have 2 rows which have been eliminated to be completely zero. So I had 2 equations which carried redundant information from the first 2. So if I write these equations back in the system form, what I see is I can write x1 and x2. Again, these are the variables that correspond to the pivot elements. I have the x1 pivot and the x2 pivot. These are actually called the basic variables. I can write those 2 variables in terms of the others, in terms of x3 and x4. So x3 and x4 are both free variables. So I have 2 variables which are free to take on any value, and they will determine the 2 basic variables, x1 and x2. So that's what we do. We just let them take on values. So we just make up variables. X3, we'll let that be s. x4, we'll let that be t. So then our solution, x1, is going to be minus s minus 2 times t. x2 will be minus s plus t. And then, as we wrote here, x3 is equal to s and x4 is equal to t. So when we have it written in this form, now we can break it apart into the sum of 2 different vectors. So we factor out the s and the t, and we find which 2 vectors we'd have to add together. So just looking at the s variable, we write down the coefficients of s in each of these terms. So here the coefficient is -1, here -1, 1, and 0. There's no s down in this row. And then we have the coefficients of the variable t. -2, 1, 0, there's no t here, and 1. And so since s and t are free to take on any values at all, what that means is that we can take any linear combination of the vectors -1, -1, 1, 0, and -2, 1, 0, 1. Right? Any value of s and any value of t means any linear combination of these 2 vectors, and that will provide a solution to this system. I encourage you to go ahead and take your favorite linear combination, 2 times this one and 3 times this one. Make up some numbers, calculate the result, and then show that they satisfy these equations. So that's the end of today. When we come back, we're going to talk about solving the matrix equations.